Here's a superposition problem where we're trying to find the electric field, the total field, with two different source charges. Another thing that's interesting about this problem is they give you a coordinate system, so really all of our drawings are effectively going to be the same. They orient us assuming a coordinate system along the positive x-axis. So your picture then should have something like this with an x-axis, and there's our y, and this is the positive x to the right. And so now we can draw our charges on there. We have our origin located here. And in this problem, we have charge A is 0.03 meters from the origin. So let's say that's right here. We'll call that charge A. And charge B is 0.06 from the origin. Both are from the origin. So I'd go out just as far here, and there's charge B. So we can orient ourselves this way. And then I want to know what's the field at the origin. So we're going to throw our positive Q right here and start to draw what our fields are. We know that A has a charge of positive 5 microcoulombs, and B has a charge of negative 3 microcoulombs. And so those positive and negatives are going to help us determine the direction of the field at the origin. A is bigger than B as far as the amount of charge, and it's closer. So I expect a lot bigger arrow from A. It's both closer to the charge, and it's a bigger amount. And so when I draw A's arrow, it better be a much bigger arrow than B. And since Q is positive and A is positive, I'm going to draw an arrow pointing to the left to represent the field of A acting on Q. And B is further away and weaker. It's also negative. It should attract the charge a little bit. So there's the field of B. And again, if I want the total distances, we know that 0.03 gets us to A. B is located at 0.06, so 0.06 gets us all the way to B. So now I think we have the information we need. Let's calculate each field independently. The field of A is going to be K, which is 9 times 10 to the 9. The charge of A, which is 5 micro, is times 10 to the negative 6. And the distance to A is 0.03 meters, and we'll square that. The field from B is going to be 9 times 10 to the 9, our constant. The charge of B is 3 times 10 to the negative 6. Again, I'm leaving the sign out. I'll deal with the signs with my picture, and it's twice as far away, 0.06 squared. And so I'm going to pull out my calculator and punch in these numbers. Alpha K, I have stored, times 5 second e to the negative 6 divided by 0.03 squared. And I get a value of, how many zeros? I got 4, 7, 5 times 10 to the 7. 5 times 10 to the 7 newtons per coulomb. And I'm going to go second enter. I'm just going to edit this a little bit. This is 6 away, and this is a 3. And I should get something even smaller. There we go. There's 7.5 times 10 to the 6. Oops. Newtons per coulomb. We're going to be adding these as vectors, and let's look at our picture. Well, I drew an arrow to the left for A, so I'm going to put it as a negative, and an arrow to the right here, so I'm going to make it positive. And when I add these numbers together, all right, if I have 5 second e to the 7, well, that's my negative one, negative 5 second e to the 7, plus 7.5 second e to the 6, I get negative 4.25 e to the 7, right, which kind of makes sense, right? Negative 4.25 times 10 to the 7 newtons per coulomb, which really means I could say negative in this case because it's the positive axis. So my field, this actually would be a correct answer to say negative. Or you can say that the total field at the origin is equal to 4.25 times 10 to the 7 newtons per coulomb away from, or we can even say towards the negative x direction. In the negative x direction is probably the best way to describe that, because they gave us our convention by referencing the positive x-axis. So the negative x direction would be the best way to describe that.